Hello 108 students, Mr. McCue back here on section 1.1. I'm going to go ahead and work on objective 5, and we are on page 3. Okay, so we're kind of going to get moving here. The book has covered terms that hopefully you kind of remember. This next one, objective 5, is called absolute value, and this was a way for mathematicians to kind of describe the distance that you'd be driving, whether you're coming from the left side or the right side of the number line. And what I like to do in class, I like to turn around and say we're right here at 0 at our CWI main campus, and if you lived 5 miles east and lived in Meridian and you got up and you had to drive into class and the campus, you would go 5 miles on your odometer. However, if you had a friend who lived in Caldwell perhaps, or Nampa, 5 miles west, and that student got up and drove towards the campus, he or she also would go a positive 5 miles. And that's the concept of absolute value. So mathematicians wanted to come up with symbology, and that's what's happening a lot in mathematics, is you got to learn to read the symbology and translate it. Is we used two vertical bars to represent absolute value. Okay, so there's the magic, there's the secret. If you see two vertical bars, you're talking about absolute value. If you put a -5 into the chamber, that's what I like to call the absolute value chamber, and think of this as like, too bad you can't see my hands here, think of this as a magic trick with the hat. You drop the chamber, meaning that the sides come down, and when they always come down, you get a positive 5. And it seems kind of silly, but if you had an absolute value chamber and you had a positive 5 in there, if you drop the chambers, you still would come up with a positive 5. So that's what the definition of absolute value is all about. So basically, when you evaluate them, whatever goes inside the chamber, it always comes out a positive. Excuse me. Now, a couple real quick examples here. A positive 13 goes in, 13 comes out a positive. Look at the negative. 2 comes into the chamber, drop it, drop the chamber, and you come up with a positive 2. Remember, if you see a number, if you do not see a sign associated with it, it's always assumed to be positive. Check this one out, number C. A negative comes in, that would come out as a positive 8, but the negative drops down, and you're left with your final answer of -8. Okay, a couple ideas there. We're going to move on real quick to objective number 6. And we're going to deal with inequalities, use of inequality symbols right here. Inequality means they're not the same. Something is less than or greater than another two things. It's a comparison, and so we've got some symbols here. Key thing here is to try to remember to read these from left to right when you see the symbology. What I remember these are, you might remember the alligator. The open end is the big end, and the pointy end is the small, and it doesn't matter what direction it's going. So here's the smaller number, there's the bigger number, here's the bigger number, there's the smaller number. Now, if you see these standalone, looking at it from left to right, we say this is the less than symbol, this is the greater than symbol. But if you look at it between two numbers here, you say 3 is less than 5. Here, this is saying -1 is greater than -4. Now, if that messes you up a little bit, don't forget, draw your number line. Here's 0. Find -1. Find -4, and ask yourself which one's bigger. Now remember, always on a number line, everything to the right is big. Everything going to the left is small. And so -4 is less than -1. Or you could read this as -1 is greater than -4, and because it's to the right on the number line. Okay. Other thing that happened here is you can have a case where you can have less than or equal. I think what happened was mathematicians got lazy. I like to put the two equal signs on here to help you remember it. I think we used to do it and they just dropped it. So you got to realize that if you see one single horizontal line, that's the same as an equal sign. So this is less than or equal. It's a condition. You have to satisfy both of them, such as x is less than or equal to 7. That would be all the values 7 and smaller on the number line. We're going to graph these here on the next page, so I'll show you there. This phrase right here is greater than all of x such that x is greater than or equal to -3. Notice how I read that from left to right. All of x such that x is greater than or equal to -3. And don't forget, you can have a condition where you use an equal sign with a line through it, and that means it's not equal to. And we use that every once in a while. So you've got equal sign, that means not equal to it. Kind of like when we have the whole no smoking or no Ghostbusters and all that kind of good stuff for the movies. Okay, keep on moving here. Objective 7. Kind of finish up this page here. Graph sets of real numbers. Now, if you've had 025 with us, you're going to remember these. When you're graphing for greater than or less than, you're going to use parentheses to represent not up to but not including. I like to think of this as the open circle in the old days when we used to graph these. Instead of using closed circles to represent the number, we're going to use a left bracket or a right bracket to represent greater than or equal to or less than or equal to, and I will cover this on the next page. Finally, I mentioned this before a couple page back, but interval notation, infinity is either a negative infinity, which means you're going towards smaller and greater and greater larger negative numbers, and you can also go towards positive infinity. You do not have to put the plus sign on there. Using the set notation here, if I ask for all real numbers, that would be represented by the parentheses. Now, this is not ordered pairs from graphing, but parentheses tell you here that you go all the way. The smallest number here is negative infinity, but you can never achieve infinity. Therefore, you would not use the bracket. You would not use it. So you always use parentheses with infinity, negative infinity, going all the way up to a positive infinity, and you can never achieve it because you can always add 1 to it. I think of this as the universe, if you want to look at it symbology-wise there. It goes on forever and ever, and as we know, our physicists are telling us our universe is expanding all the time. Okay, class, that's it for page 3. We'll move on to page 4 here, and I'll see you there in a minute.